So, hello everyone. Today we will be starting the second lecture of this module, that is measurement of process parameters. So, if you recall what was discussed in the last lecture, the first thing we discussed why we need instrumentation, why you need to monitor different process parameters. Then we discuss how we can classify these parameters into physical, chemical and biological categories, and then next we discuss, once we are going for monitoring, how can we classify the type of instruments which are being used to monitor these parameters. So, continuing further, today what we are going to discuss for monitoring of key parameters, how they are monitored, what is the working principle, and then we will be discussing further this measuring those process parameters. So, bioprocess monitoring, as if you recall the last lectures, we will be continuing further. Here it says, if you want to operate at a optimum conditions, it may be optimum temperature, optimum pH, optimum RPM, optimum dissolved oxygen concentration. So, in that case you need to monitor those parameters, and if there is any deviation, so that need to be controlled in order to maintain the optimum conditions. If you are monitoring, what information you will get information on how fermentation is progressing. So, you are going to get, let us say, biomass, you are going to get data biomass with time, whether biomass is increasing and reaching to plateau or it is not increasing. Similarly, if you are monitoring the substrate, you can see whether substrate is there or not, whether its rate of, particularly let us say this is T and yes, you can see the rate of substrate depletion, whether it is depleted or not. So, it gives the information about fermentation progress. Further, it indicates the harvest time. When biomass has, let us say you are having T versus X, when biomass has entered to the death phase, you should know this, which this is indication of the harvest, or the substrate concentration has reached to 0, it means there is no further bioprocessing or biochemical reactions are ongoing. In addition, if you see some unexpected trend, then you can think of there may be some contamination or there may be some other changes in the process, and that requires some remedial measures. So, this indicates monitoring is very important, and for that you require the monitoring equipment, and further we will be discussing the how it is integrated with process control and optimization. Then once you are going to monitor, there are three different type of sensors. One is inline, second is online, and third is the offline sensor. Inline means they are integrated into fermenter and value are directly transmitted to the control systems. Online, they are connected to the bioreactor, but the data manually need to be entered into control systems. So, in case of both inline and online, the sensor is integrated or connected with the equipment. Third is in the case of offline, where we need to take out the sample, then you have to analyze in a laboratory settings. So, here the sensors are outside or external, and you have to take out the sample and analyze it. So, in this way we can classify whether a particular monitoring is being done in inline mode, online mode or offline mode. Further, it can be also classified as penetrative sensor, sampling sensor and non-contact sensor. So, as I told, particularly in the case of inline sensor, they are directly inserted into the bioreactor, for example, pH electrode, dissolved oxygen electrode. Sampling sensor, they works on withdrawn sample, you take out the sample, for example, the exhaust gas analyzers. And non-contact sensors, they do not touch the fermenter broth or the gas. For example, this tachometer, you are monitoring the RPM of a stirrer, or the load cell, you are monitoring the weight. Now, there are certain factors which are important in the monitoring of these process parameters. First is response time. It means the response should be quick enough before there is significant change in the process parameter, because whatever we are discussing here, we are dealing with the live systems. So, all the process parameters are changing with time. So, the response time, it should be quick enough, so that there should not be a significant time till we get the result. Sensitivity and accuracy, this is very important, because everything depends on the how accurate is your data to take proper control measures. And next is the ease and speed of calibration, because after certain time intervals, most of the instruments need to be calibrated in order to ensure the data are correct. Stability and reliability, it should be stable under working conditions. At the same time, because once it is coming directly into contact of bioreactor, there are chances of fouling, there are chances of interacting with other biomacromolecule, let us say proteins. So, in that case, those interactions should not affect its performance. Then output signal, whether it is continuous or intermittent. And next one is what is the material of the construction of your monitoring instrument, how robust it is, and it is very important, if you want to reuse it, can we sterilize it, because once you can sterilize, it is very easy to reuse for multiple cycles. And another parameters that is very important is the maintenance and the cost. It should not be very expensive, at the same time the maintenance should be easy. It should not happen that for the breakdown it taking a long time for the maintenance. So, here I have listed the process sensor and the control function. Let us say if you are monitoring the temperature, what will be the control function? Either heating or cooling. Similarly, if you are monitoring the foam, if it is high, then you have to go for the foam control. If you are monitoring the weight, it indicates there is change in the flow rate. You can monitor directly the flow rate as well, rather than monitoring the weight. In case of chemical, let us say you are measuring the pH, then you can think of whether you need to add alkali or you need to add acid. Redox potential, this additives to change the redox potential for a particular oxidation reduction reaction. Oxygen, it indicates is there any change in the feed rate of aeration system or oxygen supply. Exhaust gas analysis, similarly it indicates what is the rate of gas generation. Medium analysis indicates change in the medium composition, particularly the utilization of substrate with time. So, here you can see how some of these key parameters are being monitored, particularly you start with the temperature, the most common one. So, there are various methods like mercury in glass thermometer, bimetallic thermometer, pressure bulb thermometer, thermocouples, electric resistance thermometer and thermistors. Similarly, for the flow measurement, either it is a gas flow or the liquid flow, and for biochemicals or metabolites, there are ion specific sensors, enzyme and microbial electrodes are there. They are also integrated with biosensors. The near infrared for the analysis of these biochemicals, and mass spectrometer for analysis of chemicals. In addition, there are other monitoring equipment like pressure monitoring, pressure control, agitators of power, RPM or rotation, foam sensing and control. You can measure the weight, microbial biomass measurement and control of diesel oxygen, exit gas analysis, pH, it is very important, pH control and measurement, redox and carbon dioxide electrode, because CO2 is the most common gas in a off gases. So, let us consider the temperature that is most commonly used and most commonly monitored parameter in a bioreactor. It play a key role, particularly you go for both microbial or enzyme system. When you go for microbial system or enzyme system, both have the optimum temperature. So, how we are going to monitor this? Mercury in glass thermometer, bimetallic thermometer, pressure valve thermometer, thermocouples, electric resistance thermometer, thermistors, and now we also have this infrared thermometer. So, you might have seen this application of infrared thermometer during this COVID period, when you used to measure the temperature by this IR guns. And in bioprocess, this metal resistance thermometer and thermistors are widely used. So, mercury in glass thermometer, this is used at lab scale, particularly they are fragile and it has limited use. So, we all of us must have seen this mercury in glass thermometer. This is the usual thermometer. So, it has the mercury and mercury rises, and that directly indicates what is the temperature. Next is this electrical resistance thermometer. They are also known as resistance temperature detector, RTDs. So, this is based on the resistance of pure material like platinum with increase in temperature. So, this is the property of material. If you increase the temperature, there is change in the resistance, and though resistance can be measured, for example, by a Wheatstone bridge circuit. So, let us say resistance for platinum wire is 100 ohm, and that will change in the case of an increase in temperature. So, for this method it is highly accurate. The accuracy is plus minus 0.25%, sensitive to small changes, and no restriction of distance between sensor and the display. It is compact and particularly enclosed in a stainless steel to provide the robustness, and as I told, it is used in a large vessel. Next important one is the thermistors. So, this is made of semiconductor materials, for example, oxides of iron, nickel and other metal, while this RTDs, they are made of pure materials like platinum. They are characterized by a large resistance change over a small temperature change. So, RTDs were highly accurate, and these thermistors are very sensitive as compared to RTDs. They are stable and also accurate, and reading can be obtained similar to the last one like Wheatstone bridge or electronic circuit. They are also compact and applied at large scale bioreactor operation. IR thermometer, also known as laser thermometers, temperature gun or non-contact thermometers. So, they are non-contact device that measure temperature by detecting the thermal radiation emitted by an object. So, these are the common type of monitoring instrument for temperature. So, here you can see comparison of different temperature monitoring devices. So, mercury in glass thermometer, they are simple, accurate, but they are fragile, not suitable for automation. Pressure bulb thermometer, they can measure at a remote locations, but they are bulky and response is slower. Thermistors, they are very sensitive and fast response. Disadvantage, the response is non-linear. Biometric thermometers, this is another class where you are going to have this biometric, and being biometric, the both the metal have different thermal conductivity and different expansion coefficient with temperature. So, we are going to see the bending of those biometric materials at different temperatures. So, they have disadvantage like low sensitivity and less accurate. Another example is the thermocouple. They are wide, applied for wide temperature range, robust, but they are less accurate and they are prone to drift. So, it requires frequent calibrations. And RTDs I have discussed, they are high accurate and stable, but they are more expensive. The next parameter we are going to discuss is the flow rate. So, in the case of flow rate, we are going to have both liquid and gas. So, for flow rate, the most common is we apply the Bernoulli principle. If you just see, this is the Venturi tube. So, it works on the principle of mass balance. So, it says there is a potential energy, kinetic energy and pressure energy delta P. At any given point, this energy is the constant. So, kinetic energy is defined as 1 by 2 rho v square plus potential energy is rho g h plus P pressure, that equals to the 0 or this is the constant. So, at any given 2 points, we can apply this Bernoulli principle, and to get particularly what you are interested in the velocity, and if you know the velocity, we can calculate the flow rate. Flow rate is F is equal to area into velocity. So, there are different setup. This is, you can see the Venturi, another is the orifice plate, a thin plate, rotameter, Coriolis, there are magnetic flow meters as well. In addition, there are ultrasonic waves are also used to measure the flow rate, and this is the traditional way to have a metering pump, where different pump can measure those flow rate, because we know what is the flow rate of a pump. Similarly, for gas, the most common one is the area meter or rotameter. This is the example. So, it is having a float, and depending on the flow rate, this float will reach to the another equilibrium, and we can read the reading over here. In addition to rotameter, there are another devices for the gas, that is the mass flow meters. And another type of measurement, it can be the heat carried by the gas, because this is the gas flow rate. So, they can also get heated, and depending on the change in the temperature, we can calculate the flow rate. The most common one is the rotameter for the gases, and this Venturi meter for the liquid flow rate. Similarly, the pressure measurement, so depending on the pressure value, it can be moderate pressure, high pressure or low pressure. So, for moderate pressure we might have seen in the lab also the manometer. So, one side is connected to atmosphere, one side is connected to your device, and depending on the difference in the H, you can calculate P is rho GH or P is mgh. In addition, there are another pressure gauges which have elastic elements like diaphragm, capsules, Burden tube, spiral and helix. This is the figure of the Burden tube. So, it says it is connected with the pressure, and when you apply the pressure there is a deformation in the Burden tube, and when it is deformed this tube is connected with a pointer, and the pointer changes its position, and there is a reading dial. So, from there you can directly read the pressure value. For high pressure we go with the electrical resistance pressure gauge, because there is change in the resistance. For the low pressure, particularly less than 1 millibar, we go with McLeod gauge, Pirani gauge or ionization gauge. So, this is the image of Pirani gauge. So, here you can just see you are having a thermocouple here, and there is a heated filament here, and once you pass the gases, depending on the pressure there will be change in the temperature, and that can be calibrated in the terms of pressure. Next is agitator power and rotational speed. So, agitator shaft power, they are measured by simple motor watt meter. For a small scale we can go with torsion dynamometer or strain gauge, and the rate of steering, the most common one is the tachometer. Next comes the foam sensing and control. So, there are different way to sense the foam. There will be change in the conductance. If let us say you are having the insulated stainless steel electrode, so once it touches the foam there will be change in the conductance. Similarly, there can be change in thermal conductivity, change in the capacitance. In addition to that, there are ultrasonic method also to see the level of foam, and there is a rotating disc. So, that also works sometime as a foam breaker. So, you just see this is a bioreactor and this is your foam sensor. So, what it will do, once the level of foam touches this sensor, it will go to detector, it will go to timer, and finally there is a control device, that is a pump. It will start the flowing the anti foam to the bioreactor, so that foam level will further go down. So, you are going to have this foam probe, then foam contact. So, it activate the anti foam pump or valve, and there will be timer. It ensures the mixing before it re-triggers, and in addition to this whole device there is a foam breaker, like a kind of a mechanical device. Once level of foam goes up, it breaks the foam. When you go to this monitoring the biological agents, so many times what we found that real time estimation is different. So, traditionally how we used to monitor biomass, in fact if you remember the previous module where we discussed the growth profile of microbes, there also we have discussed how to monitor the biomass in terms of weight or in terms of number, both. So, traditional one can go with dry biomass spectrophotometer to measure the observance, or one can use the counter to count the number of cells. But now one can also use this fluorimetry. So, it measures the NAD or NADH level for biomass monitoring. So, NADH fluorescence used to track glucose uptake and mixing etc. So, it indicates whether a biomass is active, and depending on the biomass growth, this rate of uptake will vary. They are high sensitive, stable, and it can be sterilized in the case of in situ applications, and it is also used for monitoring metabolic changes. Next is dielectric spectroscopy. This measures the cell biomass by capacitance, particularly the cell membrane response, and this capacitance correlates linearly with the biomass in suspension. They are also sterilizable. Capacitance probe are available for yeast and bacteria monitoring. Next very important parameter is dissolved oxygen. So, we have also discussed briefly monitoring of dissolved oxygen in the topic of aeration. So, it says when we are going to monitor this dissolved oxygen, we monitor the partial pressure, and partial pressure can be converted to concentration using concentration into total pressure. There are three main methods: tubing methods, mass spectrometer probe, or electrochemical. So, here you can see electrochemical detectors works in a galvanic or polarographic mode. In the case of polarographic, you are applying a fixed voltage and monitoring the change in the current, and here you are monitoring the change in the current. So, there are some difference in this, because the change anode, if you just see, there is a lead, and from anode you are generating 2 electrons, they are going to cathode, and it is further generating the hydroxyl radicals. Here in the case of polarographic, you are having Ag plus Cl counter electrode. So, electron is generated here, and at the cathode the electrons are utilized to generate the hydroxyl radicals. So, you can combine the reaction of both at anode and cathode and write the overall reactions. Further, if you just see in both the cases, there is a Teflon membrane, and this thickness of membrane affects the time response to the sensor, because through membrane only this oxygen is penetrating and reaction is taking place at the cathode. So, you just see at the cathode reaction is taking place in the presence of oxygen. So, you can just see the image here, this galvanic and polarographic. You can see this anode is AgCl, and here the anode is, you can say, the lead. So, galvanic electrode, they are small and low cost. Polarographic electrode, they are more accurate, and but they need polarization, because they need certain voltage. Here it is important that the performance of these electrochemical sensors are affected by pressure change, gas composition, or variation in the temperature. So, now there are new techniques are being developed, particularly the fluorescence based sensors, and they works on the base principle of oxygen quenching, and they are supposed to be more stable for long term applications. Next very important parameter which are regularly monitored is the pH. So, typically this pH is monitored through electrochemical method. So, there are pH electrode, and which is having the measuring electrode. So, this detects the hydrogen ion activity, and if you know the hydrogen ion activity, we can calculate the pH value. And there is a reference electrode. So, as compared to change in the potential difference due to change in the solution pH, we are able to measure the pH. So, the difference in the potential is related with E naught plus 2.3 RT upon NF into pH value. So, we directly get the pH value and it is monitoring the difference in the potential. This is nearest equation. So, here there are certain challenges also, the leak of electrolyte, as this bulb is directly coming into contact with fermentation broth, there is a issue of fouling and some challenges of sterilization, because this many times steam sterilization may not be recommended. And for the metabolites or even substrate, this NIR spectroscopy are commonly used. So, the wavelength range is 460 to 1200 nanometer, and they are used for rapid, continuous and batch analysis of fermentation broth, and they can monitor even fat, biomass. If they are measuring this teichoic acid, they are the part of the cell wall of the biomass. They can measure the antibiotic, one example of product, can measure the enzymes, glucose and lactic acid. So, for example, fat analysis by a fiber optic sensor in the fermenter wall. So, once we are going with this NIR spectroscopy, the assay time reduces from hours to minutes. So, we can very quickly analyze these parameters. Another parameter is the mass spectrometer, which is particularly applied for the analysis of gas and other volatiles. They can monitor other compounds like oxygen, carbon dioxide and methane. So, this equipment is equipped with capillary gas inlet and membrane inlet, and once it is injected inside this mass spectrophotometer, they detect the mass of the sample. So, further for this biological parameters, biosensors are used. So, as you know, the biosensor is nowadays lot of extensive research is ongoing. So, how they are defined? Biosensors, they are having the biological materials, it acts as a detection element. In that case, the fabricated sensor is known as biosensor. What is the sensor? Typically, it says it converts the change in the physical and chemical property to detectable signals, which can be recorded by an instrument. So, what are the component of a sensor or biosensor? There is a biological element, it goes to transducer. Transducer means the results are converted to a measurable signal, then amplifier, the output of transducer is amplified, then it go to the processor. This converts the value of biosensor response into analyte concentration by means of standards prepared by a calibration curve, then monitoring, that is a display device. So, we are going to have biological elements, that is substrate of interest or analyte reacts with these biological agents and causes the physico chemical changes. So, these biological agents, it can be enzymes, it can be even microbes. So, based on the type of transducer, we can have electrochemical biosensor, piezoelectric, optical or thermal biosensors, and they have potential to analyze carbohydrates, alcohols, organic acids, amino acids, fatty acids and even different microbes, bacteria and viruses. So, it has a vast potential. What is the advantage? As it is, we are using the biological agent, it is very selective, or the specificity is very high. So, here you can just see how glucose is analyzed. Glucose the biological agent is glucose oxidase, it converts glucose to gluconic acid, and once you are going to get this gluconic acid and H2O2, further H2O2 reacts with this reduced dianisodine, and then it gets oxidized. There is it was colorless, now it becomes the brown color, and further this brown color in the presence of sulfuric acid, it becomes this pink color. Another option is if you are having the sucrose, then sucrose first need to convert it to glucose. We are using the invertase enzyme. Invertase converts sucrose to glucose and fructose, then further glucose oxidase is applied to convert glucose to gluconic acid, and then here you can apply this peroxidase enzyme as we discussed above. So, in this way this glucose and sucrose biosensor works. In addition, one can have this microbial sensor for process fluid. For example, acetic acid and ethanol, this organism implied is Trichosporan brassicae. For ammonia, you can have Nitrosomonas or Nitrobacter species. For cephalosporin, the Citrobacter fruendi. Formic acid, we have Clostridium butyricum. For glucose also this Pseudomonas fluorescens, and for glutamic acid equally. So, there are different methods through which they are immobilized, and how they monitor. There is for example, simultaneous oxygen consumption, there is a liberation of H ion, production of H2, the CO2 production and detection method. If it is oxygen, you need to have oxygen electrode. If it is H ion, you are having pH electrode. If it is CO2, you are going to have the CO2 electrode. So, what I mean to say, apart from enzyme, this biological agents can also act as a biological agents for the detection. So, I will stop here. So, what we discussed today, this various monitoring devices for physical, chemical as well as biological parameters. In the case of physical parameter, we discussed temperature, we discussed the pressure. In the case of chemical parameter, we discussed pH and dissolved oxygen, and in case of biological parameter, we discussed the biomass, as well as we discuss particularly the application of biosensors for detection of different biological agents. Thank you so much.